Alright, so how many of you guys feel super comfortable with Altium? Cool.
Just no, not really.
Well, we could fill in some of the gaps. What about you guys? I know you guys have never used it, so we'll try to breeze through some of the basics and then hit on some other stuff. So the learning objectives today are creating a parts library, creating a footprint library. When I was first starting with Altium, it gave me the biggest problem because there's a thing where you can link. Altium makes every part you could ever want, but because we go to CU and don't have our own licenses, we can't access it. So you have to build really every part that you want. So we'll go over that because we'll be building a lot of parts, and then dealing with the kind of the design rule check system and how to make a rule. And then finally a little bit about signal integrity. It won't apply to us too much because we're not getting up in the gigahertz range, but you can kind of see why when you're looking at the UART channel why it's like spiking super hard, and it relates a lot to RF. So, all right, we're gonna switch this up a little bit and just go over the signal integrity stuff first. So, why does stuff ring? And that is because there's reflections. So, when you send a signal down a line, it essentially starts off whole, and when it's not matched, say you have an impedance change, so you're sending it from 10 ohms out the pin into a 50 ohm transmission line, and all signal traces can be modeled as transmission lines essentially. Their values are super small, so that's why it only matters when you get up to the higher speeds, but essentially it just bounces back and forth, and that's why you get that ringing across the line when you put a no-scope onto it. So how do you fix this? Well, there's two types of ways. You can add a resistor to the front or the back. So what you want to do is you want to keep the characteristic impedance the same across the entire line. So say you have say this is your endpoint. You're just trying to communicate over UART, and essentially you just have a point-to-point, but the endpoint into the other IC is like 1,000,000 ohms. So there's obviously going to be a pretty large reflection back, and as it gets in higher speeds, it's going to be more severe. So what you do is you put a resistor here. Say this is a 50 ohm transmission line, then you're going to put a 50 ohm resistor right here. So it keeps the characteristic impedance the same all the way across the line, and you're just reading at this point. So that's kind of another way. Same thing right here. You can do the same thing. It just depends on what your application needs. Usually the easiest one is to do the end termination. So that kind of leads us into good board design. So length is everything. So there's a lot of different examples I can think of when designing PCBs, and essentially the most efficient way to do anything is to have kind of, say this is your IC pin, as short as possible to the other IC pin. If it's high speed, you can match it, or you can do a differential pair. We won't go into that, but essentially that is the most efficient way. Now, you get even more ringing even at lower speeds when you have kind of like, they're called stubs. So now you have another pin that needs to read the same UART channel. I wouldn't know why, but say you have 10 devices and they all need to read the same UART channel to get the same data. Well, now you're going to have reflections here coming back and here, and it's just gonna make the signal worse. So that's a big one. Keeping lines short for any data communication protocol is going to be a big thing when it comes to board designing. So when you're thinking about designing, say, our next board, we want to keep the lines as short as possible, and usually you want to keep the UART TX and UART RX matched, just for simplicity reasons. The other big one was ground discontinuities. So I don't know if you noticed when we were designing our last board, our signal went straight there. Oh, it kind of did this weird. Our traces were not best laid out, but when the signal returned, when you have a ground, I can just show you on Altium. So when you have, I don't know how to zoom without. All right. Well, it's bigger there. So right here is where I could see a lot of problems. Our ground and signal paths, when we started routing these lines, it breaks up our signal return path. So essentially the signal, when it's getting to the via, say this is a via, it needs to come all the way back up to here. And so what it's doing is it's doing this weird, instead of just going like that with the ground plane, it's doing this weird like go around everywhere, go back. And so that increases the resistance, and you're gonna get voltage swings on your ground plane, which is never good, because then your signal, or the IC doesn't know the threshold changes, and then you can get bit errors and everything like that. So when you're designing things, it all starts with a layout, and you're gonna wanna group things together. And essentially, by grouping things together, you can reduce the amount of, or the length the return signal has. And so for high-speed applications, really you want to group things as tight as possible. So that's a little bit of what I want to talk about. We can go over some. Let's see. Oh, the last thing was vias. So vias cause impedance changes. So when you're routing signals, keep vias to a minimum. Yeah, a signal speed increases, vias cause impedance shifts, then you get more reflection. Also, I can't remember the physics, but it can completely attenuate your signal if it's like a quarter wave or half wave, or half the wavelength is half. It can completely just I don't know how the physics work, but he briefly went over it, and it was like 6 months ago.
Smith chart.
Yeah, exactly. So, let's see. So when I'm designing, I'll give you guys a kind of an idea when I'm designing a board. I always know, unless special circumstances require, I know that big parts or high power parts, so usually switching power circuits or just like any power application, usually isolated away from the digital side. Really big if you're doing high power switching stuff, because that creates a lot of E&M radiation that could affect, say, your Wi-Fi shit. So isolating your power, and usually what I do is if you're having any problems with thermal relief or underneath any IC or anything, usually polygon and small little vias will cure that. For anything else, you probably need a heat sink. So when I'm designing a board, I usually don't worry. I usually do a little thing where, like on this board, usually what I do when I know I need to connect a signal to ground, I change a via to the minimum amount of, or the minimum hole size that advanced circuits will allow us, and then I just do this. I don't know if you guys can see it, but
Which is what for our case, for our deal? 13 mils or 15?
yeah, I think
15 mil.
let's see. Pull it up. So hole size 15 mils, diameter 28 mils. That'll be huge. That way we don't have to change all the vias on the backside.
Yeah.
So I know we didn't connect this part, thermal relief, for our voltage regulator, and then so I'll go into a little bit about polygon. I know I'm jumping all over the place. trying to machine gun you guys with information. So this will. So when we're talking about polygons, the biggest thing you're going to want to look at is this plane section right here, and you can make specific rules for each component or the whole board. And so the big thing you need to know about polygon fills is this right here. So what this is going to tell you is if it is relief connected or if it's full connected. Full connected or direct connect is great for thermal relief, but it's going to be a bitch to solder. So if it's a huge pad, you have to have a huge wattage soldering iron. You have to like push it on there for a while. So just keep that in mind. Direct connect, it's not as great thermal relief, but it also is easier to solder. You guys know, I guess, what were you taught when routing boards? Was he just like, all right, go at it?
Pretty much.
All right. So when I'm routing a board, I usually don't use the auto router. I usually just route it by hand. That way when I'm debugging, I know exactly what signals go where, and it's easy to reference. It takes a lot more time, but overall your signals are going to be maybe not cleaner because computers are good at what they do, but you're going to know exactly where it's going to be, and you're going to be able to deal with any problems that come up in an easier manner. So what I do is on the top layer, I route signals horizontally, and then route bottom layers vertically, and that basically you just use vias to jump across the lines, and that'll reduce the amount of conflicts you have. Because I don't know if you guys have ever run into a problem where you just can't route anything anymore. Your top layer is saturated with routes, and then I don't know what to do, and you can't get underneath the bottom layer. Go, I'll just throw another layer on it. But that's going to add $33 or $400 or so. This will reduce a lot of the conflicts, and it usually makes the board look better. So, let's see.
I kind of have a question.
Yeah, go for it.
So, how cluttered? When do you take that? When do you make that decision to jump up to a 4-layer? Like, how much can you impede your ground plane before you're like, there's too much going on in my ground plane. I need to bump this up to like a 4-layer.
Yeah, that's a good question. I think it really depends on the speed of your design and how well the return paths on your ground plane are relative to the power source. So, and that this might not be the best answer, but for me, when I think about it, I'm thinking, because we've done quite a few simulations, so I go maybe simulate the return plane on. I'll get back to you on the program, but I would simulate it if I'm having any doubts, and essentially, your question was, when do you jump?
Yeah, obviously you don't want too many discontinuities in your ground plane for high-speed designs, but some are okay. But you use a software to simulate data integrity?
Yeah. Yes.
Okay.
If you have any doubts, if we have any doubts, I can get you guys the software, and essentially you can just simulate. It simulates ground bounce, it simulates signal integrity across the line, characteristic impedance and stuff like that by changing, by layout, and then also you can change the characteristics of the PCB material, and also look at inductance and stuff like that.
Okay.
So that's one way. If you design a lot of boards, you could just look at it. I'm assuming good design practices.